Hi everyone, good day. Today we are going to see the next lecture in the course Cryptography Network Security. The topic that I am going to cover in this lecture is Introduction to Modern Symmetric Key Ciphers. In that we are going to see about block ciphers in this lecture. This course is developed by Jawaharlal Nehru Technological University, Kakinada, in support with Andhra Pradesh State Council of Higher Education. Myself, Dr. M. Sitaram, working as Associate Professor in the Department of CSC. Lekkireddy Balreddy College of Engineering. So coming to the today's topic, that is block ciphers. So block cipher are the basic ciphers which take input as n-bit plain text and convert this n-bit plain text by using any algorithm or the help of a key into an n-bit ciphertext. The same vice versa will be happening at the receiver end also. The receiver end as this block cipher takes n-bit ciphertext, use the same key and convert this n-bit ciphertext into the n-bit plain text. So this process where we are converting plain text into ciphertext, we call it as encryption. The process where we are converting ciphertext into plain text, we call it as decryption. So one thing we need to remember about block ciphers is here we should use the same key on the both sides, the sender side, while we are using the encryption. Whatever the key that we have used here, we are showing it as a k-bit key. Whatever the k-bit key we have used, the same k-bit key should also be used at the receiver end. The decryption algorithm must be the inverse of the encryption algorithm, and both operations must use the same secret key. I told you, they must use the same secret key. Now, when you are considering of block ciphers, the blocks that we are considering should be of n-bit. Now, what happens? See, whenever we are sending a data from a sender, consider A, and to a receiver B, he always doesn't send the same size of n bits. Always doesn't say the size of n bits. Maybe the data may be less than n bits sometimes, maybe the data greater than n bits. Now what we need to do is always remember the block ciphers accepts data of the size only n bit. If I call the block size that the n is 64, then the data that we are supplying to the block cipher, the data always should be of 64-bit size only. If it is less than 64 or it is greater than 64, it won't accept. So here comes the concept called as padding. Why we need padding is to make everything data that is transferred between source and destination. While we are encrypting it by using block cipher, we should make it as an n-bit blocks. Similarly, while the data is distributed to the receiver, while it is converting into the plain text, again we need to supply the n-bit blocks. Now, what is the concept of padding? So padding helps us that, if, for example, if consider we need to supply an n-bit data. We need to supply an n-bit data to the block cipher. For example, if I have n minus 4 bits of data, that I have received from the receiver. Now I cannot supply this n minus 4 bits data. Now what I'll do is I will pad in this. I'll add 4 bits of zeros. I'll add 4 bits of zeros to the data. Now, if I add zeros to the data, it will not affect the existing data. Now, what happens if I add four zeros? Now, this n minus 4 plus 4 bits. Now, this data becomes n-bit data. So, I can easily supply this n-bit data to the block cipher. This is a situation when we are having data less than n-bit. Sometimes I told you, there may be two situations where we may get n-bit block at that position. At that point of time, we don't have any problem. Simply we'll take this n-bit of data, we'll apply to the block cipher. Simply there is no question here. But what happens if you are receiving data less than n? I told you, we simply add how much of bits are missing from this n bit, that many zeros will add, nothing will happen. Okay, but when we get a data more than n bits, what happens is we need to divide this data into blocks. We divide the data into blocks, and each block should have n bits. For example, if dividing that, we have got some residue. We got some registers. We are left with some bits. For example, consider n as some 8-bit. Consider n as some 8-bit. Consider. Generally, it starts from 64, 128 like that. But consider, for example, consider it is an 8-bit block. Now, the data I have received is 72. Consider the data I have received is 72, which is greater than 8-bit. Now, what I'll do is I'll divide this 72-bit data into blocks, n-bit blocks, that is 8-bit blocks. So I can divide this exactly into 9 blocks. I can divide exactly into 9 blocks. So then each block will have 8 bits, no problem. But consider I have got an data of 80 bits. Now I got an data of 80 bits where my block cipher accepts only 8 bits. Now, here also no problem. I can simply divide it into 10 blocks. 10 blocks. So when the given data is exactly divisible by the n, then there is no problem to us. But when we got a data which is not exactly dividable by n, then there is a problem. So for example, if I consider I have received 86 bits, the data I need to transfer from sender to receiver is 86 bits, where I need to convert this 86 bits data, where I need to convert the 86 beta data into the ciphertext. And at the receiver side, I need to convert this again into the plain text. This is what I need to do. Now, what is the size of my block is? Size of my block is 8-bit. Consider size of my block is what? 8-bit. Now, what I need to do? I need to divide this 86 bits by 8. Now, what happens? I'll get 10 blocks of data. For the 11th block, what is the problem is I'll get only 6 bits. For the 11th block, I get only 6 bits. So at this position, what I'll do is simply I'll add 2 more zeros to the data. So I got 10 blocks of data. In the 11th block, I got 6 bits and I added 2 more bits. This is also called as padding. Now I added 2 bits. Now what happens? This also becomes a n-bit block. This also becomes a 8-bit block. So totally I have 11 bits of data, blocks of data. Now I'll convert one block by block and I'll convert here. Okay. At the plain text size again, I will remove this and I'll get the 86-bit data. This is what happens in the block ciphers, and we consider as what we call this concept as called padding. When we are having bits data less than the n-bit, or when you are having data greater than the n-bit, then we'll use this padding. So generally, the block size that we consider will be maximum. Generally, it will be 64, 128, 256, or 512. General the block size that we consider. Okay. Now let us solve this problem. No. What the problem is saying, how many padding bits must be added to a message of 100 characters if 8-bit ASCII used for encoding and the block ciphers access blocks of 64 bits. Now, we need to first derive mod m. First, we need to derive what is mod m. So, how we need to derive mod m is, so what is the length of the message? We have 100. The length of the message is 100. And what's saying this 100 have characters. We have 100 characters. Now we need to represent these characters in the, we cannot transfer, or computer will not understand ABC, no? We need to convert them into some binary language. So what is saying, these characters is of 8-bit, of each is of 8-bit. Now what I need to do, so totally I have 100 characters, each character of 8 bits. So totally I have 800 bits. This is our mod m. So this is the size of the message. Now, what is my block cipher size? That is block size. So block cipher accepts blocks of 64 bits. So my block size is what? 64 bits. So according to the formula, what should be that? Mod m plus padding. Whatever the pad I do, it will be should be 0 mod. Now, if you follow, 800 is not exactly divisible by 64. 800 is not exactly divisible by 64. Now, what we need to do is we need to find out how many bits we need to do padding. How many bits we need to do padding. So, if you observe 64 into 12, 64 into 12, we are going to get 768. So this is exactly divisible. Now, if I subtract 768 from 800, so what is it? 32 bits. 32 bits. That means I have an excessive of 32 bits. I have an excessive of 32 bits. Now, if I want to make this remainder 32 bits dividable by 64, so I need to add them to make a 64. So if I need to add 32 more bits, I need to add 32 more bits. So according to this, if I make the total message as, so actually I have 100 message characters, each of 8 bit. So totally I got 800 bits. 800 bits. Now this is not divisible by 64. So what happens is I'll get 12 blocks. I'll get 12 blocks. For the 13th block, I'll have only 32 bits. So to make it this block as a complete block, I need to add one more 32. Now totally I'll have 13 blocks, which can be easily encoded by using the block ciphers. Blocks. This is how the padding works. This is how padding works. Now we consider these block ciphers as permutations group. As permutations, we apply more permutations on the block ciphers, right? So if we want to apply it as a permutation group, first we need to derive the size of the key. Whether we are what is the size of the key? Whether we are using full key size or we are using only partial key size. So generally we can consider these block ciphers as substitution or transposition block cipher. So what is substitution transposition block ciphers is, if you are implementing a block cipher, if you are implementing a particular block cipher as a substitution cipher, if you are applying block cipher as a substitution cipher, here we will simply substitute a value. For example, generally in the substitution cipher, in the traditional substitution cipher, we'll take A and we'll take a key value, consider key value as 3. We exactly replace A with the alphabet, which is 3 units distance. So B, C, D. So we replace with D. But in the block ciphers that we are considering, we are dealing with only bits, either 0 or 1. So we can say that in the substitution or transposition cipher, we replace a 1 bit or 0 bit in the plain text can be replaced by either 0 or 1. So 1 bit can be replaced either by 0 or 1. 0 or 1. Similarly, a 0 bit can be replaced either by 0 or 1. We are simply replacing the value. Here we are simply replacing the value. Whereas if you are following or if you are constructing a block cipher as a transposition cipher, here we will simply change the values. Okay? The bits are only reordered. There is same number of ones in the plain text in the cipher text. Whereas in the substitution cipher, for example, if I have 1, I can replace with 0 or 1. So I cannot determine whether in the plain text 1 is replaced by 0 or 1 is replaced by 1. We cannot determine. But whereas in the transposition cipher, for example, if I have 3 ones and 4 zeros, 3 ones and 4 zeros, here the value of number of ones will be same, the number of zeros will be same. Simply these will be rearranged. Maybe these may be rearranged as 0 1 0 1 0 1 0. Now if you observe here in the transposition cipher, the same values we have 111 4 zeros, but they are rearranged. This is what transposition cipher. That is, we'll have same number of ones and zeros, but they are rearranged. But whereas in the case of But whereas in the case of substitution, if I consider the same triple one, 4 zeros, symbol 1, 4 zeros, now this one I can replace with 0, this one I can replace with 1, this one I can replace with 0 again, this 0 I can replace with 0 and 1 and 0 and 0, right? 0 and 0. So this is how. See, if you observe here, number of zeros are 5 and number of ones are 2 only. So there is no real image. This is substitution. Instead of 1, I can replace 0 or 1. Instead of 0, I can replace 1 or 0. So for the hackers or the people who are doing some crypt analysis, what is the message that is being transferred from source to destination, they will not understand. So with what has been substituted. But if you are following a transposition cipher, they can easily understand that the message that being transferred between sender and receiver have total number of 3 ones and have total number of zeros, and they'll choose the permutations, and they can easily find out what is the data that is being communicated with the sender and receiver. So nowadays in the modern block ciphers are designed by using only substitution ciphers because of their inherent characteristics. Transposition makes the cipher vulnerable to exhaust such attacks. I told you, if I apply an attack on the data that is being transmitted using transposition ciphers, I'll come to know that there are 3 ones in the data and 4 zeros. Now I'll apply permutations and I'll get what is the data that actually being transmitted between source and destination. That's why the modern block ciphers are designed as substitution ciphers. So now I told you about the full key and partial key. Now we'll see that. So if you consider full key size ciphers, that key is long enough to choose every possible mapping from the input to the output. Every possible mapping from the input to the output. So, but actually, the modern block ciphers, they'll use only partial keys. Modern block ciphers uses only partial keys. But to know the importance of partial key, first we'll see what is the about full size keys. Full size key ciphers. So we'll consider full size key transposition block ciphers as well as full size key substitution block ciphers. For example, consider a full size key transposition block cipher. A full size key transposition cipher only transposes bits without changing their values. So it can be modeled as an n object permutation with an n factorial permutation. So we doesn't change the values. We are going to change the positions. We are going to change the positions. So the number of possible permutations, we can consider it as n factorial. When we have n factorial possible keys, so the key should be of the size log n factorial base 2. Log n factorial base 2. Okay. So why? Because we can have n factorial possible keys. So the size can be derived by using log n factorial base 2. Here we consider the upper bound. On this one, we consider the upper bound. So we know upper bound, how we are going to represent, right? Upper bound we are going to take. Now let us consider this example. Where we are having an 3-bit block transposition cipher. A 3-bit block transposition cipher. So here, if we have a 3-bit data, if I want to transpose it, what I need to do is 3 factorial permutations I can have. 3 factorial permutations. So what is 3 factorial? 6 things I can have. 6 different permutations I can have. So what are the bits I have? 1, 2, 3. Now, as I have 3 bits of data, now I can consider it is having 3 factorial permutation. That is, I can rearrange these 3 bits in 3 factorial ways. That is, 3 factorial is equal to 6 ways I can rearrange this. So let us see the 6 ways. What are the 6 ways? So 1, 2, 3 is the one way. 1, 3, 2. That is, I am fixing the position of first value. Then I can change second and third. So here in these two, what I am doing is I am taking 1 as the first position and the second, the third are changed. Here I am taking 2 as the first position and 1 and 3 are changed. Here I am taking 3 as the first position and 1 and 2 are changed its position. So totally I have 6 possible positions. Okay, 6 possible positions. So what should be the size of the key? So we came to know that we are going to take the upper bound of this log n factorial base 2. So what is log n factorial for us? Log n factorial is 3 factorial in this example. Log 6 base 2. Log 6 base 2. So what is the value of log 6 base 2? So I can take it as I can take it as 3 into 2. I can take it as 3 into 2. So log 3 base 2 plus log 2 base 2. I can take it as log 3 base 2 and log 2 base 2. Now, what is these values of these things? This will be consider 1.2 or something plus log 2 base 2 is 1. So we're getting 2.2. So as I told you that we will take the upper bound. If I make this 2.2 as an upper bound, the value will be 3. The value will be 3. So the size of my key is what? 3 bits. The size of my key is what? 3 bits. So this is how we take the transposition block cipher. Okay, this is how we take it in the transposition block cipher. This is how we derive the size of the key. So we have this many number of permutation tables when we are using the transposition block cipher with the full key size. Now, if we consider full size key substitution block ciphers, so we can model the substitution cipher as a permutation if we can decode the input and encode the output. Decode the input and encode the output. We know about decoder and encoder. So decoder is what? It takes n number of inputs and it produces 2 power n outputs. We know about decoder. Similarly, the encoder, it takes 2 power n input and it produces n outputs. It produces n outputs. That we can make it. So decoding means transferring an n bit integer into 2 power n bit string with only a single 1 and 2 power n minus 1 zeros. I'll tell you an example. The position of single 1 in the value of the integer in which the position ranges from 0 to 2n minus 1. So whatever the decoder that we are seeing here we are taking an n bit as 3. Here we are taking the n bit as 3. So according to the decoder encoder concept, so what we'll have? We'll have 3 into 8. That is have taking n into 2 power is 8. We'll get 8 object permutations. We'll get 8 object permutations. And if I apply these permutations to the encoder, as it is 2 power 3, it will give 3 output. But if you consider these 8-bit object permutations, total I'll have 8 factorial permutations. As I have 8 object, 2 cube, that is 2 power n, I'll have total 2n factorial permutations. I'll have total 2 power n factorial permutations, right? So 2 power n is here 3. So I'm taking as 3 bit. Now, how can I decode this into? This into 8. So let us consider if it is 2 cube. So I'll have from 2 cube is equal to 8. I'll have from 1, that is 2 power 0 to so on 2 power n minus 1. So I'll have totally from 0 to 7. I can represent this 8 as 0 to 7 values. I can have this 8 as 0 to 7 values. Now, how I am going to represent this 0? So consider 3 bits 0. So 3 bits 0. Now I'll represent this by using an 8 bit. So 0, 1, 0, 2, 0, 3, 4, 5, 6, 7. Now I'll make 8 bit as 1. So it represents that this 8 bit value represents that the value that I have decoded belongs to 1. The value belongs to 1. Now, if I have 0, 1, 0, how can I represent is 1, 2, 3, 4, 5 zeros, 6. And what is the value of 1? 2. So I need to make it as 2. So I'll make it as, so if you count from this, 1, 2. So 0, 1, 2. So I should make this as 1. I should make this as 1 and this will be 0. So this is how I'm representing the value of 2. The value of 2. If I take it as 101, what is 101? What is the n01? The value 101 is 6. So how I'm going to represent is, I'll take this as 1. Right? So 1, 2, 3. So I'll take it as 1, 0, 2. So 0, 1, 2, 3, 4, 5, 6 as 1, and the next value as 0. So this is how I'm going to represent using the substitution cipher. Now, if you observe here in the substitution cipher, the key size is of, how many permutations are possible? How many permutations are possible? 2 power n factorial permutations are possible. So if 2 power n factorial permutations are possible, the size of the key should be log base 2. Log base 2, 2 power n factorial. Here also will take the upper bound. Here also will take the upper bound. Here also will take the upper bound, right? Okay. So log base 2, 2 power n factorial. So it is log base 2. It is log base 2, 8 factorial. It is log base 2, 8 factorial. So the 8 factorial value with respect to log 2 is almost equal to 16. So the number of bits we required is 16 bits. The number of bits we required is what? 16 bits. Okay. So if we take 16 bits, the number of possible things is 2 power 16. The number of possible different keys is 2 power 16. Again, it will be equal to 2 power 70. Right? So if you consider, okay, if we consider it equal to, so a full size key and bit transformation cipher or a substitution cipher block cipher can be modeled as a permutation, but their keys are different. Their key sizes are different. So for a transformation cipher, the key size is log base 2 n factorial bits. For a substitution, the key size is log base 2 2 power n factorial bits log. Okay. Now, why we are not choosing is, for example, if we consider here, what are the total number of things like possible is 2 power 16. 2 power 16. 2 power 16. So 2 power 16 value is 65368. I told you, no, 2 power 16 is the possible 2 power 65368. But out of these 65368, we are choosing only 40320 elements. 40320 elements. Okay. So we will not use any key full size keys. We will only go for partial size keys. So actual ciphers cannot use full size keys because the size of the key becomes so large, especially for a substitution block cipher. So for example, if we consider a common substitution cipher in DES which uses a 64-bit block cipher. So if the designators of DES had used a full size key, so here it is 64-bit block. If it is 64-bit block, as we are using a substitution cipher, so the number of permutations possible is what? As we are using 64-bit block, the number of permutations available is 2 power 64. 2 power 64 factorial number of permutations are possible. Now, if these many permutations are possible, then what happens is the key size will be log of 2 power 64 factorial, 2 power 64 factorial base 2, which is equal to 2 power 70 bits. But as we are using the same size in the DES? No. The size of the bit key size we are using is 56 bits. 56 bits, which is very small fraction of the full size key. This means that DES uses only 2 power 56 mappings out of approximately 2 power 70 possible mappings. So generally we'll go for only for the partial size key ciphers. Why we are not going for the full size is because we cannot accommodate, and it takes more amount of time to convert this full size keys and apply the permutations. Remember, always we consider only partial size key ciphers. Now, in the next topic, we'll see. We cannot say that everything in the block cipher depends upon the key only. There are some components. A block cipher, the block that we are showing, no, the block cipher within the block, there may be many components. So initially we have seen the block, right? So this is the block where we apply the encryption. So while we are applying the encryption within this block cipher, it have an algorithm, but this block is combination of many components. This block is what? Combination, or this block is built by combining many